Good morning, everybody. So my name is Chi-Chuan Qiao. I'm a Hobart endowed professor from South Dakota State University. I appreciate John to give me these opportunities. So that I can present some result. My group is doing, especially related to agriculture sensors, probes, and their integration into weather soil station for real-time field monitoring in precision agriculture. So today I also brought my PhD student with me, and then his name is Ahmed, and he has done a lot of work, specifically lab-based work, and also test some of the sensors and the weather station in the field. So just in case if there are some questions specifically about, how the technology is being developed, how the technology has been tested in the field, and then Ahmed can help me for that. Basically, I will introduce, what is precision agriculture and also how we can use Internet of Things to play in the precision agriculture, and then what is current problems in the field for especially for farm management, and then with the motivation objective. Later, I will talk about the technical achievement we have uh, obtained, especially for the phosphate and some other related sensor probes we developed from the labs. And then the sensor network we also developed from the uh, soil or weather stations, and then followed by conclusion, future work, and acknowledgement. Precision agriculture is important, especially how to manage the farm, how to improve the yield, how to improve the sustainability, and also how to lower the costs for farmers or producers. So all this precision agriculture depends a lot on data and data analysis in order to achieve what precision agriculture mean. So basically, the precision agriculture approaches can, support, improve farmers or producers' decision-making processes, manage and control the primary agriculture factors such as soil fertility, soil quality, water, weed, pest, disease, or biodiversity in the field. Uh, and also, there's problems for the manual collection of data, which will require a lot of labor work and also create a lot of incorrect things, inconsistencies. For example, I have some discussion with a professor from plant science at SDSU, and then he told me that during summer, majority of his students or postdoc have spent a lot of time just going to the field to collect the data, spend the whole day there, and then not much data collected. So this actually motivates us why we start this work by creating the sensor network for real-time data collections. So this is actually a good reason why we start this project in collaboration with our collaborators from agriculture college. So here I show the figures here. As you can see here, there on the field you can have different technologies, right? From the drones, from the point contact sensors, and also sensor network get the data. The data will be collected and then transport to the cloud, like Amazon cloud service, and then with that, the data will be validated and then will be placed in the data warehouse. After that, we'll do a lot of data processing to get the data supporting, to make the data supporting systems, to help the farmer have decisions. To process the data, there's a lot of things here. I'm not sure how the picture shows. There's a lot of tools here like machine learning, deep machine learning, also artificial intelligence. All these tools will be used to process the data, to model the data, and then get the solution and then get the answer to the farmers or the growers, and then the farmer growers use this data and then provide feedback back to our system, how we can improve our system to be more accurate, to be more timely, depends the lead or what the requirement, what conditions the fields or the farms look like. So here I just give a big pictures what's the things we are doing. And then the other thing we use a lot for these sensors, we based on Internet of Things, especially when we deal with a lot of physical devices. Think about there's a field is huge, and then we need to install a lot of low-cost sensors and also all the data processing or data collection, acquisition tools there, and then all the device need to be controlled to be managed in a better way that it all function where we need the Internet of Things collect all the sensors, and then or the sensors with each other, or the sensors with the base load, and then the super load, and then the clouds. So that's why we involve a lot of Internet of Things of this technology here. Below is a figure shows the examples, like if you try to get data from the car or from the locations, from the conditions, and then you get all the data to the clouds, and then you have processing, and then finally provide decisions to whatever application that we need. So this just examples there. I think we can do the same thing for the sensors in the field. And then another big piece is the wireless sensor that works. That's another technology we use in the field, especially if we have different kind of sensors. Later I will show us sensor station. We have 9 or 10 different sensors used in the field, and then how we can collect all the sensors together, how we can get the data together. So here I show the network here. If you can look at here, maybe I should use a pointer here. So the pointer here, I have the sensor node. If you look at this red dot, or the sensor node, the sensor node can be regarded as a microcontroller with different sensors like moisture, humidity, soil information, phosphorus, nitrogen, any other type of information you try to collect, and then all these dots shows that can be a single microcontroller bind to many different sensors. And then once the sensor gets the data, the sensor will transfer the data to the base load. The base load can be enabled to collect with other sensor loads by LoRa technology or by wireless, depends applications. And after that, or the base node collect the data from, or the base node here collect data from the sensor node, and then the base node will get the data to the super node. So the super node actually have the collection with the internet. So the super node collect all the information from the base node. The base node get the information from the sensor node. So the super node gets the super node also function as internet gateway. So the super node get all the data to the clouds. And then that's the first point, how to get the data acquisition or data collection there. So basically, in the next slide, I will first talk about the sensor probe, and then I will talk about the wireless sensor that works. So about the problem, why we need to develop these technologies, I think there are multiple reasons. Number one is that right now there may be some real-time monitoring tools for the weather conditions or soil properties, but all this is quite expensive. And then also they do not include, most of this information. Sometimes producers, are interested, are really needed. And then the second reason is that field-specific informations make it difficult for a precise decision of precision agriculture or crop management. So we try to create the sensor systems that can collect the information from the micro environment in the field. For example, we recently worked with Emmanuel from plant science. He's also a professor from extension. He's worked on the white mold, and then we developed a sensor and the sensor network for him to collect information, specifically in some field that can easily cause problem for the white mold, especially when it has high humidity and the temperature is pretty high, and then the wind is not that big enough, to dry the field. And then the other reasons like soil nutrient information such as nitrogen, phosphorus, water limit the production of the accurate food production. And then we can provide sensors to get a specific soil nutrient information there. And then also deficiency of soil nutrients, that can cause problems for the crop's function and time growth. That's another reason we focus a lot of these sensors that can sense, that can get the data from the soil quality or soil fertilizer information. Okay, based on this, I will talk about the sensors that the first sensor will be about the uh, phosphorus sensors, and we are also developing some nitrogen sensors, but the result has not been ready. And then we also did some work in the heavy metal sensors. That's something I'm going to show as well. So about the motivation, I think from the problems we can see that design, development, or testing of customized and cost-effective weather soil sensor stations, for short we call the WSSS, to collect real-time soil properties, climate conditions, and also crop information. And then to address these problems or to achieve based on these motivations, we'll collect the field growers exposed in real time for making right decisions based on site-specific information collections. And we'll also establish the effectiveness of wide-mode disease forecasting system based on the leaf wetness and other variables. So as I mentioned earlier, first I'm going to talk about a few technologies. One is for phosphorus sensors, the other is for heavy metal sensors. So in our lab, we developed a technology called printed electrode sensors. It's actually, here shows the device. It actually have the 3 electrode, counter electrode, working electrode, and the reference electrode. It's based on electrochemical technologies. And then what we did, if you look at here, the middle side here, this is the working electrode. It's actually the printed carbon. Since the carbon is printed, carbon material itself is very inexpensive. There's no cost. And then, but the sensitivity is not high enough. That's why we integrate these carbon materials, this guy, the carbon electrode with silver nanowires. So here, if you look at here, there's some silver nanowire there, and then the silver nanowire incorporate with this carbon electrode is significantly improve the sensitivity for the sensors, especially when it's used to sense the phosphorus. And then the magnesium here, I'm not sure how many of you are chemists. Here I just showed the magnesiums, how you can sense this phosphorus. If you look at the phosphorus, it's here, right? Depends how many phosphorus ions you have in the soil or in the water, and then when you have more of these phosphorus ions, you have more reactions. Based on that, you use the electrochemical method. You can just measure the current. You apply the voltage, you do the electrochemical cycling, you will see that as you have more, higher concentration of these phosphorus ions, you see a higher concentration, a higher current. And then if you plot all this together, it shows a linear relationship between the current and the concentration of the phosphorus ions. And here, you see here, I don't have this silver nanowire incorporate. Later, if I have silver nanowire incorporate, you see the signal increased significantly. See here, you have like 150, right, microampere. Once you have the silver nanowire, you can increase that about 4 times to 600. And then we published this work on the IEEE sensor geolers here for phosphorus sensors. So if you plot this concentration, the relationship between the concentration of this phosphorus ions and the current, and then you'll see there's a good linear relationship between the concentration and the current. So this red plot shows that there's no silver nanowire incorporate. The black shows the dark curve shows the 0 nanowire incorporated, you can see the sensitivity is significantly improved with this 0 nanowire incorporated. And then another technology we developed, I think we work with some faculty member from agriculture engineering. They are working on the water. So on the water, they care a lot about this heavy metal like mercury ions in the water. That's why we developed technology. Actually, this one is actually graphene oxide, also 0 nanowire nanocomposite, and then we use that on this glassy. Here we use platinum. We also use on glassy electrode, and then I may not go too much details as we may run out of time. So this just shows that there's a with we sulfur modify the electrode, use this 0 nanowire and also graphene oxide, and then we use this electrode to make these sensors, and then the sensor can work pretty well with the mercury, and then there's a specific chemicals like the COH group, the carboxylic group here, that can bind only to mercury, and then that's why we can find the mercury from the sensors. So here I show some results. The concept is the same. We use the 0 nanowire to improve the sensitivity. So the black one here, let me show this dark plot here is the sensor without 0 nanowire. The blue one is with this 0 nanowire. And then you can see here the sensitivity improved a lot. And then if I do the concentration, finally, if you change this in the concentration of this mercury in the water, you'll see the current density increases, the current increases. And then you plot that together, you see there's linear relationship between how much mercury you have in the water, how much current you get. It's very precise measurement here. Here I show the selectivity. For example, I have mercury, I have lead, cadmium, copper, tin, silver, sodium, others here. You see this selectivity is very high for mercury compared to other metals. And also, for the reproducibility, that means I have the 3 different sensors measure the same concentration. It shows pretty well, very reliable measurement, high reproducibility. And also if I do the repeatability, I have the same sensor measure different measure at different time. You see, it's 3% like repeatability, 2% reproducibility. It's very reliable measurement here. And then we also did this in the real tap water. We add amount of this mercury into the water, and then we try to test it. And then you can see the recovery or the accuracy is 90%. If we add like 1 nanomolar, I can find 0.9. If 10, find 7.9. 70. So it's pretty, it's a pretty reliable measurement here for the mercury. And then next, I'm going to move to the wide sensor networks. So here, as I mentioned earlier, we have the sensors like the phosphorus sensors, heavy metal sensors. We can bury that in the soil, and then the sensor will be enabled have the NORA technology. So the sensor will have a microcontroller here, send the data through NORA, and then to the super node, and then from the super node you can collect to the server, to the cloud, and then the end user can get the data. The data can also be processed. And then here I think I probably already talked about these figures. We have, sensor node here, base node, collect data from sense node, base node get the data from sense node, and then send the data to the super node, get to the gateway, and then to the end user. So here shows there's what is the super node we developed look like, and then this sensor node, what the sensor look like. You see I mentioned there's microcontroller here, and then you can have 9 different sensors collected, right? And then also there's the NORA modules and real-time clock, so you can know when the data is collected. And then here shows the specific information like this can be for soil sensor load. For example, I have microcontroller. I have this 9 different sensors. You can see temperatures, humidity, wind speed, wind direction, rainfalls, sun radiation, soil moisture, and we can add more data like phosphorus, nitrogen, near wetlands, especially important for the wide mode. And then if we just think about this, that can be our sensor load, and then can also be a base load if you have LoRa here. And then you can also have this direct connect to the super load, and then with power supplies, and then the super load get data directly to the internet through the through the gateway. The gateway is it is integrated with the super load there. And then here I show the real system we developed. This you can see here. These are different sensors, 9 different sensors at four here. But some of these can be have dual sensors there. And then this is we have next slide. I'm talking about the power supplies. Where's the okay? So you can see different sensors, and then the power supply from solar panel. There's a solar panel here, and then also there's a battery here. Just in case sometimes you don't have enough sunlight, or at night time there's no sunlight, there's a battery. The solar panel can charge the battery. Battery can get back to this whenever you need the power without sunlight. And then we have this SD card that for local data, storage. And then we have this real-time clock tell you when the data is collected. And then LoRa is it's a receiver from. And then if there's a larger sensor node far away, the LoRa send data from that sensor node will have this LoRa sender. And then this super node will have the LoRa receiver there. So here shows the microcontroller have different sensors collected. You see all this, the interface with different sensors. And then here shows the power supplies. You can see here. And then there's one thing that I would mention here with this a voltage converter here that can help to improve the battery lifetime. And then here we developed the 4 sensor stations, and then install 4 different locations in South Dakota. One is Eureka, another one in Varga, 2 in Sioux Falls. And then we have last season we collect 500,000 data points, and then right now the plant science, plant science faculty members are working with this data to improve their decisions or whatever change they want. And here I show different regions. One is in north, and then this Eureka, Varga, Twin, and so forth regions. All these farms right now are owned by SDSU. Yeah. And then once we got the raw data, we validate the data. Because sometimes even the sensor can collect data wrong. We need to get rid of this wrong data, incorrect data. That's why we do this raw data validation before we get data, collect in this data warehouse. And then from last season, for example, we collect about 63,000 data points, and then there's only 800 data that was incorrect. And then the same thing, for 2 different. This for first super sensor station. There's another sensor station is similar. We get about 500 data points wrong out of the 63,000. So if you look at that, there's about less than 0.01% wrong or incorrect data. And then once the data is collected to the cloud, I think we are also developing this data modeling, so get the decision right out. And then producers, the farmers can use a cell phone. I show the different cell phone here, a different kind of. This is we have a system here. The farmer can create an account. Right. Once they create an account, they can access the data, find different data there. And then we are also developing the modeling system. I think this modeling, once a model is developed, it can get the results to the farmers, producer directly. And then here's the real data and access. If you log into the website, you can see at different times. This will be the date, time, and then you see the temperatures, humidity, wind speed, all kind of different data you can get at different time, at different locations. Here is the location, latitude or longitude, shows the locations on the field. Yeah, based on this, we actually last year we got an award from EDI University Center for commercialization. Especially we try to commercialization these tools, and then there's about like $725,000 thereabouts for this commercialization, and then also the state have another 725 as a match. The total we have about 1.4 million there for us. Yeah. Now I think let me conclude. We have developed the phosphate and heavy metal sensor probe. We also developed 4 sensor stations that can get real-time data collected from the field to the farmers. And the preliminary results shows the system is very effective, practical, and can enable the farmer, the producer, to make better decisions in their operation. So in the future, I think we try to improve the load communication to superload for long range use in LoRa, and also build a fully remote control soil barrier sensor node. Sometimes I think farmers learn about that. How can you get the sensor in the field when the tractor pass by? It will not destroy the sensor or sensor station. That's something we are working on now. That's also future work, and then we'll control the station or control the sensor so that can avoid the tractors automatically. So and also improve the mobile app for collect data and building field history. And also I will submit some SBIR, STDR project. I've talked with Xiong on this. We try to meet the next deadline in October maybe. Yeah, I would like to acknowledge the funding. We got some funding from Governor Research Center, also EDI University Centers, and then we have student support by NDVI scholarship program. And then we work with different faculty members like Dr. Gary Field, Emmanuel, and also Jason Storhagen. With that, I would like to close my talk and take any questions if anyone has. Yeah.
Okay, great, Quinn. Thank you for that. And I apologize for the technical issues we had. What I was not able to communicate to you is, as your questions come up, go ahead and enter those in the chat box. And so what I'm going to do is I'm just going to read the questions as they come up, and give Quinn an opportunity to respond. So the first is from Nicole, and she asks, what criteria were used to locate the sensors in the field?
Oh, this, I think I have my student here. He has talked with a lot with Emmanuel from Agriculture Extension. I think he can answer some of the questions from your interaction with the question here. So what criteria were used to locate the sensor in the field? I can start, like for the white mold, when we talk with the plant scientist, he knows some regions which is very wet and has high humidities, and then in these regions it's easier to build the white mold for corn or soybean, right? For soybean. So and then that's where we will install our sensors. Especially we have a special sensor like the leaf wetness, humidity sensors, and then for that regions we see how this white mold is built up from there's beginning, small amount and then big amount, and then how the white mold spread. And then we try to study this micro environment in a specific field. Typically, the producers will tell us, where that's more likely to get these problems, and then that's where we locate the sensors. Did that answer the question?
We'll let Nicole follow up if it did not. So our next question is from Steve. So he says, this uses cloud technology. Are there problems with rural broadband limitation or poor coverage? I guess rural broadband internet issues. Is that a potential concern?
Do you mean the problem of internet availability in the field?
I think the issue is kind of more broadly about connectivity with rural, so maybe a data problem potentially.
Yeah, large amount of data, the internet may not strong enough to cover so big data point.
Yeah, because for the supernode where should be connected to the internet, we use hotspot very close inside the box that will over internet 24 hours 7 days. But the other sensor node that located far away from the supernode, we use LoRa technology that will doesn't need to use internet because it based on radio frequency. So we don't need any internet across the field. We just need it in one spot for the send collected data from other sensor nodes to the cloud.
Okay, thank you for that. Next question is from Alan. How might this affect nutrient runoff? Can it help reduce phosphorus or nitrogen in water sources?
Yeah, it can. The sensor itself, like the sensor and sensor probe we developed, works best in the water environment. So in water sources, we can apply the sensor just in the water or close to the water, and then to track how this phosphorus run off from the land to the water, to find the tracks. And then if we can apply sufficient number of sensors, and then for a certain period of time or turn to track this, I think we are able to do that. We actually did some discussion with David Clay before about this.
Okay, thank you for that. Next question is from Anthony. Can you clarify where you are in the development process? How close to commercialization?
So right now, if you look at the superload is actually ready. We have made 4 prototype. We installed that in last season. I think our collaborator from plant science was very happy with the results. And then he's asking us apply this again. Right now, we are working with South Dakota GOED, Government Office for Economic Development, and then we also try to get funding from the SBIR. We try to commercialize this. I think we can share this more prototype at this moment, right?
Yeah. There are many professors, they asked us to before.
Oh, there's okay. At this moment, there basically we have a lot of extension, faculty members. They try to ask us to build more for them. I think that's a good show. For the sensor station, I think it's ready to be commercialized. Anyone want it, we can build for them now.
Okay, thank you for that. Okay, next question is from Paul. He asks, did you say this works on solar, the whole system? Can you talk about number of sensors in the field?
Okay. Do you want to start?
Excuse me, do you mean the sensor in each sober node?
No, this is solar. The solar panel provides the power, right, to charge the sensors, right? And then so the whole so the supernode is powered by the solar panel, and then there's a lead acid battery right underneath. This only for the superload, for the data collection, data transmission to the internet. There's other places where the sensor load. They do not. Battery, they do not use solar because they consume very small amount of power. So that's just based on the battery. And then the data communication, we use LoRa. LoRa is known to consume very little amount of power. So for that point of view, only the superload is powered by solar. the sensor load, the best load, will be buried in the field. So that's actually use the batteries.
Yep.
That can be coin batteries, since the power we use is so small for these sensors. So the battery can run a long time. Yeah.
Okay, great. Thank you for that. Next question from Alan. Is this best for field crops? Is this best for field crops?
A field crop. This field crop.
Field crop, yeah. Like soybean or wheat.
Yeah. Why not you?
It looks like he just clarified row crops. So yeah, so maybe corn, soybeans.
Oh yeah. We are tested all our devices in soybean, because it is one of the very important crop in South Dakota region. Also, it is affected by white mold, so that's why we focus on soybean. But we can, work with other crops like corn, for example, or wheat, or.
Okay, thank you for that. The next question, what are the models used for predictions to support the decision making?
Yeah, we actually used like 4 different models or 4 different machine learning techniques, like uh, KNN, Nurse Neighbor model. Also, we used the decision tree model and support vector machine also based model. So we got, when we test all different statistical models based on machine learning, we got almost the same result, more than 92% of accuracy from all those models to predict. We use this model to predict leaf wetness, because it is the key factor of white mold disease.
Okay, thank you for that. Scrolling down here. Okay, it looks like one more question. Do you see the sensor network scaling in the manner that allows using adequate testing sites within a field to manage variable soil test levels and various soil types?
Yeah. For example, if you want to monitoring like soil moisture or soil temperature, we use different sensors in different depths, and we got real data, in real time. So it's easy to monitoring any other parameters if you have that sensor available.
Okay, thank you for that. Next question. Do you have any assessment of the efficiency and accuracy of the system?
The data. I think you have the data validation.
Yeah. The only problem we got with the system is very, tiny. The transmission, because when we collect the data, we are in the field. We don't know if the batteries work okay, or is any environment factor can affect our system. So that's why we installed local storage SD card in the each sensor node. So when we collect data, first we save it in the SD card, then transmit to the cloud. We got like maybe 0.001 percentage error, that data don't receive it by the cloud. That means lost in the way between the super node and so I can see more than 98% the system work perfect.
Okay, great. Thank you for that. Let's see if we've got any other questions. I'll give just a couple moments if anybody's got anything else they want to ask here. Okay, it looks like no. So Quinn, it looks like we'll wrap up the webinar, but before we do, any parting thoughts?
No, not at this moment. I think, yeah, if anyone, anyone is interested in the system, we can provide more information, and then we can also build the system for you guys if anyone have interest to use that.
Okay, great. Thank you for that. Kind of near the top of the comments is a link to the NCRCRD website. So the presentation and the slides recording of that will be available there. Also, I've got Quinn's email and my email up there if you want to connect with us directly. So thanks again for you in the audience, and thanks to our presenter, Quinn from South Dakota State University. And with that, we will wrap up our webinar.
Thank you. Thank you all.